Welcome to the deep dive. Have you ever stopped to think how, I don't know, the same element can give you that awful skunk smell?
Oh yeah, unmistakable.
And also the amazing smell of a truffle, the really expensive
It's
ones.
kind of wild, right? And yeah, that element is sulfur.
Exactly. So today we're doing a deep dive into Chapter 27 of Organic Chemistry, the second edition by Clayden, Greaves, and Warren.
A classic text.
Our mission really is to get under the hood of some elements you might not think about every day in organic chem. We're talking sulfur, silicon, and phosphorus.
The sort of unsung heroes below carbon, nitrogen, oxygen.
Right. We want to see what makes them tick, chemically speaking, how they work in reactions, how chemists use them to build molecules really precisely.
Especially things like controlling alkene geometry, that's a big one. And other key transformations.
Think of this as your guide to their strategic use in synthesis. We'll be looking at mechanisms, functional groups, stereochemistry.
And that clever backwards thinking,
Yeah.
retrosynthesis, all straight from the book.
Okay, let's jump in then. So we're all comfortable with C, N, and O. They're stars, right?
Pretty much, yeah.
But then you go down one row on the periodic table, sulfur, phosphorus, silicon. They seem similar in some ways, but how are they fundamentally different players?
Well, the really big difference, fundamentally, is orbitals. These second row elements have third orbitals available.
Which the first row just doesn't have.
Exactly.
Yeah.
No thread for carbon, nitrogen, oxygen. But for sulfur, phosphorus, silicon, this opens up a whole world of bonding possibilities. More bonds, higher coordination numbers.
Like sulfur, the book mentions coordination numbers from 0 up to 7.
That's right, 0 to 7. Huge range. And think about electronegativity, too. Sulfur. It's actually about the same as carbon.
Really? Not like oxygen, which is way more electronegative.
Not at all. Sulfur is much less electronegative than oxygen. So you can't just think about simple bond polarity in the same way you do with oxygen compounds. There's more going on.
It explains that sort of contradictory nature you mentioned earlier, skunks versus truffles.
Exactly. It could be a reducing agent or an oxidizing agent, an anion or oxidation, nucleophile, electrophile.
A real chemical chameleon. And it pops up in really important places, right? Medicines like dapsone, glutathione, penicillin, obviously.
Absolutely critical. So let's talk reactivity. Basic sulfur-2 compounds like thiols, RSH, they're pretty good nucleophiles.
Especially the anions, the thiolates are...
Thiolates are great. We call them soft nucleophiles. They tend to prefer attacking, say, saturated carbons in SN2 reactions, different preference than hard oxyanions like hydroxide.
So a typical reaction might be thiol plus sodium hydroxide, then add an alkyl halide.
Perfect example. That gives you a sulfide, RSR, straightforward SN2.
Okay, so that's sulfur as a nucleophile, but you said it can be an electrophile too.
It can. Take something like a sulfonyl chloride, RSCl. That sulfur is electron deficient. It acts as a good soft electrophile.
So it reacts with alkenes.
Yep, reacts with alkenes. You get this interesting Seglic intermediate, a three-membered ring with a positive sulfur, a sulfonium ion.
A bit like bromination, but with sulfur.
Sort of, yeah.
Yeah.
It's a way to add sulfur across a double bond. But here's a twist. Can sulfur in a higher oxidation state be a nucleophile?
That seems counterintuitive. More oxygen usually means more electron withdrawing.
You'd think so,
Yeah.
but yes, it can. Think about a sulfonate anion, RSO2. You can make these from things like tosyl chloride and zinc.
Okay.
And this sulfonate anion is actually a good soft nucleophile. It likes to attack saturated carbons, so you could react it with, say, an allylic bromide.
And you'd get an allylic sulfone.
Exactly, RSO2 attached to the allyl group. So sulfur's role really depends on its oxidation state and what it's attached to.
It's amazing. The sheer number of sulfur functional groups is huge. Thiols, thiolates, disulfides, sulfoxides, sulfones.
And they all have their own chemistry. Plus some are chiral, like sulfoxides, stable tetrahedral.
Like little chiral centers based on sulfur. Okay, let's dig deeper into one of sulfur's superpowers, stabilizing negative charges next door. How does that work, and why is it so useful?
Enogian stabilization. This is huge in synthesis. If you look at the acidity, the ppK, of a proton next to sulfur, it depends massively on the oxidation state.
So comparing a proton next to a sulfide versus a sulfoxide versus a sulfone.
Right. The sulfone is the best at stabilizing that negative charge once you remove the proton. Then sulfoxide, then sulfide.
How big a difference are we talking?
Massive. Going from a sulfide to a sulfone, just adding 2 oxygens, could drop the pKa by something like 19 units. That's enormous. Makes the proton way easier to remove.
19 units. Wow. And does that change the shape of the carbanion?
It does. Next to a sulfone, the carbanion tends to be planar, flat, like an enolate. The charge is nicely spread out. Next to sulfides or sulfoxides, it's thought to be more pyramidal.
And the reason for the stabilization, there was some debate. D orbitals?
Yeah, historically, people invoked d orbital overlap. The current thinking leans more towards polarization effects and maybe some delocalization into the CS sigma star orbital. But whatever the exact quantum mechanics, the effect is real and very useful.
Can you give us a practical example? Where was this used?
Oh, definitely. The synthesis of biotin, vitamin H, really complex molecule-length bicyclic structure.
Right.
A key step involved alkylating an anion, stabilized by its sulfoxide group. Deprotonate next to the sulfoxide, add an alkylating agent. That was crucial for building up the core structure.
Okay. And what if you have two sulfurs next door, like in thioacetal or those cyclodithions?
Even better, those protons sandwiched between two sulfurs are even more acidic. Deprotonating and alkylating dithions is really common.
This leads to that concept the book mentions, unpolling. Polarity inversion.
Exactly. Think about an aldehyde. The carbonyl carbon is electrophilic, right? Delta positive.
Always wants electrons, yeah.
But if you make a dithion from that aldehyde and then deprotonate the carbon between the sulfurs, suddenly that carbon is nucleophilic, delta negative.
You've completely flipped its normal reactivity.
You flipped it. That's unpolling. In retrosynthesis, we call these D1 synthons, or acyl-anion equivalents. It's like having a nucleophilic version of a carbonyl carbon.
Super useful trick. The book mentions a metacyclophane synthesis.
Yeah, classic example, where they needed essentially a nucleophilic version of a molecule with two aldehyde groups. Dithion chemistry was the solution.
But getting the carbonyl back from the dithion isn't as easy as with regular acetals, right? They're more stable.
They are quite stable, yeah. You need special conditions. Mercury salts work, or sometimes you oxidize the sulfur or methylate it to make it a better leaving group.
Or you can just get rid of it entirely with rainy nickel.
Right, rainy nickel chews off the sulfurs and reduces the carbon down to a CH2. So you can go from CO to CH2 via the dithion.
And sulfones, being even better anion stabilizers. They can do cool things too, like making cyclopropanes.
For sure. Anions next to sulfones form easily. You could take an allylic sulfone anion, for instance, add it to an unsaturated ester.
Michael addition first. Conjugate addition.
Yep, conjugate addition. Then the anion leftover can bite back intramolecularly onto the ester.
Kicking out the leaving group and closing a ring.
Exactly. Forms a cyclopropane ring. This was used to make methyl transchrysanthemide, part of a natural insecticide. Very neat application of sulfone chemistry.
Okay, so sulfur stabilizes anions, acts as nucleophile, electrophile. But what about sulfonium salts and ylids? How do they bring unexpected reactivity?
Right, so sulfonium salts, you make them by reacting a sulfide, which is a nucleophile, with an alkyl halide. R2S attacks Rx.
Kind of like making an ammonium salt from an ammonium.
Very similar analogy. And just like ammonium salts can be electrophilic, sulfonium salts R3S plus serol are electrophilic too.
So something can attack one of the R groups and the neutral sulfide leaves.
Exactly. R2S is a pretty good leaving group. Nucleophilic substitution happens readily.
The book gives the example of mustard gas, which is pretty grim.
It is, but it's a powerful illustration. The sulfur atom in mustard gas participates internally. It bites back on the carbon chain, kicking out chloride and forming a highly strained, three-membered cyclic sulfonium ion, an episulfonium ion.
And that thing is super reactive.
Incredibly reactive, highly electrophilic, gets attacked instantly by water or proteins, DNA in the body. That's why it's so damaging. Shows the power of that sulfur participation.
Okay, so that's sulfonium salts as electrophiles. What about ylids? Sulfonium ylids, they have that adjacent positive and negative charge.
Yeah, you form them by taking a sulfonium salt and removing a proton from a carbon next to the positive sulfur. You get this R2S plus -T species, a dylid.
Now, how do these compare to the famous Wittig lids, the phosphorus ones? That seems like a really important comparison.
It's the critical comparison because they do different things with carbonyls. Wittig lids, the phosphorus ones, react with aldehydes or ketones to give alkenes.
Right, the classic olefin synthesis.
But sulfonium ylids react with aldehydes or ketones to give epoxides.
Epoxides, totally different outcome. Why?
Driving force. The Wittig reaction is driven by the formation of the incredibly strong phosphorus-oxygen double bond in phosphine oxide. That pulls the whole reaction forward thermodynamically.
And the sulfur-oxygen double bond in a sulfoxide, not quite as strong.
It's strong, but not as strong as PO. So the mechanism goes differently. The sulfonium ylid adds to the carbonyl.
Okay, nucleophilic attack.
Forms an intermediate, and then instead of forming an SO bond and an alkene, the oxygen anion attacks the carbon, attached to the sulfur, kicking out the neutral sulfide, Me2S usually, is an intermolecular SN2 reaction.
Forming the three-membered epoxide ring. Huh. Okay, so Wittig gives alkenes, sulfonium ylides give epoxides.
Generally, yes. But there's a wrinkle.
Ah, always a wrinkle. Stabilized ylides.
Stabilized sulfonium ylides.
Right.
Ones where the negative charge on carbon is also stabilized by something else like
Yeah.
an ester or cyanide group.
Okay, what happens with those, particularly with alpha, beta unsaturated ketones?
Right. With those unsaturated ketones, stabilized sulfonium ylides often give cyclopropanes instead of epoxides.
Cyclopropanes, not epoxides. Why the switch? Is this kinetic versus thermodynamic again?
Bingo. It's classic kinetic versus thermodynamic control. The direct attack on the carbonyl carbon, the 1,2 addition that would lead to an epoxide, that's faster, kinetically favored. But for these stabilized lipids, that initial addition is often reversible. Meanwhile, the attack at the beta carbon, the 1,4 Michael or conjugate addition, that's slower, but it's irreversible.
Ah, so the irreversible pathway wins out eventually.
Exactly. The halide adds 1,4,4, makes an enolate intermediate, and that enolate then cycloses intramolecularly, kicking out the sulfide to form the cyclopropane ring.
So the cyclopropane is the thermodynamic product. Got it.
And it's not just sulfonium ylides. Sulfoxonium ylides, the ones derived from DMSO, they also tend to give cyclopropanes with unsaturated carbonyls.
Speaking of DMSO, dimethyl sulfoxide, usually just a solvent, right? But it's crucial for the Swern oxidation. How does DMSO pull off an oxidation?
Good question. In the Swern, DMSO isn't just a bystander. It reacts first with an activator, usually oxalyl chloride.
Okay.
This generates a really electrophilic sulfur species. This species then reacts with the alcohol you want to oxidize.
The alcohol oxygen attacks the sulfur.
Yep. Then a base, usually triethylamine, comes in, pulls off a proton, and this sets up an internal rearrangement. Basically in halide forms and quickly collapses.
To give the aldehyde or ketone product.
Right, and the sulfur ends up as dimethyl sulfide, Me2S, which is volatile, plus CO and CO2 from the oxalyl chloride. It's a really mild, clean, and super useful way to oxidize primary alcohols to aldehydes or secondary alcohols to ketones.
Wow, sulfur really packs a punch in synthesis. Okay, let's switch gears. Silicon. Right next door to carbon. We don't always think of it in organic chemistry, but it has some unique tricks up its sleeve.
It really does. Now, silicon and carbon, both group 14, both usually make 4 bonds, tetrahedral geometry.
That key differences.
Big differences. Silicon really doesn't like forming stable pi bonds like carbon does. Think CO2 versus IO2. Very different structures.
Right, SiO2 is a network solid, quartz.
Exactly. And bond strengths are critical.
Yeah.
The SiO bond is strong, and the Si-F bond exceptionally strong. One of the strongest single bonds there is.
Stronger than CF.
Oh, yeah. But Si-Si and Si-H bonds are weaker than CC and CH. And importantly, silicon is less electronegative than carbon.
So the C-Si bond is polarized the other way, towards carbon.
Correct. Carbon is slightly negative, silicon slightly positive. This makes silicon itself vulnerable to nucleophilic attack.
Which explains why fluoride attacks silicon so easily, even though fluoride isn't always a great nucleophile for carbon.
Precisely. Fluoride loves silicon because of that incredibly strong Si-Hef bond it can form. This unique reactivity allows for what we call SN2 at silicon.
Different from SN2 at carbon.
Yeah, it's thought to go through a 5-coordinate intermediate, a trigonal bipyramid, where silicon briefly holds on to 5 things. Carbon SN2 is strictly 4-coordinate transition state.
And this love affair between silicon and fluoride is exploited. Protecting groups.
The classic application. Silyethers are probably the most versatile protecting groups for alcohols. TMS, TBDMS, TPS, TBDPS.
Lots of acronyms.
Lots of acronyms, yeah. Basically, silicon groups with different bulky alkyl groups attached. You put them on the alcohol's oxygen, they're stable to many reaction conditions.
Now you can take them off easily with fluoride.
Exactly, because fluoride attacks the silicon, breaks the strong SiO bond, and forms the even stronger Si-F bond. And you can often remove them selectively based on the steric bulk around the silicon. Very clever.
Now here's a really cool idea from the book. The trimethylsilyl group, Me3Si, acting like a superproton. What does that even mean?
It sounds weird, right? But it's about conjugation stabilization. If you have a positive charge on a carbon beta to a silicon atom, so on the carbon next door to the one bearing the silicon.
Okay, a beta silylocation setup.
That Silly group provides amazing stabilization. It's called sigma donation or hyperconjugation. The electrons in the C-Si sigma bond can overlap with the empty p orbital of the carbocation.
So the CSI bond electrons help out the positive charge.
They help out a lot. It's a very powerful stabilizing effect. It means reactions that go through intermediates like that are highly favored and can be directed. The silicon acts like a very potent, albeit temporary, proton in terms of directing reactivity.
Okay, so where do we see this superproton effect in action?
Several key areas. Alkynyl silanes, for one. Putting a Scylla group on the end of acetylene replaces the acidic proton.
Makes it easier to handle. Acetylene's tricky.
Much easier. And it allows you to do chemistry selectively at the other end, then remove the Scylla group later. Useful for making things like alkynyl ketones.
What about aromatic rings? Aryl silanes?
Yep, you get something called ipso-substitution. An electrophile attacks the ring at the exact carbon bearing the Scylla group, replacing the silicon.
Why there?
Because the intermediate carbocation is stabilized by that beta-Scylla effect. Again, the silicon directs the substitution to its own position. This is used in Fleming-Tamau oxidations, where you replace the silicon with an OH group.
Neat. And vinyl silanes. Silicon attached to a double bond.
These are fantastic for making alkenes stereoselectively. When an electrophile attacks a vinyl silane, it adds to the carbon not bearing the silicon, generating that beta-silication.
Okay.
And then the silicon leaves, forming the double bond. Critically, this happens with retention of geometry. If you start with an E vinyl silane, you get an E alkene product. If you start Z, you get Z.
Wow, precise control over the double bond
It's
geometry?
extremely precise.
Yeah.
And then there are allyl silanes. Silicon is one carbon further away from the double bond.
C-Si bond next to the pi system.
Right. These are even more reactive than vinyl silanes.
Yep.
The C-Si bond can align nicely with the pi system. When an electrophile attacks, it usually attacks the far end of the double bond, the gamma carbon.
So the double bond shifts. Allylic rearrangement?
Exactly. Electrophilic attack happens at the gamma position, the double bond moves, and the Scylla group leaves. Again, excellent regio control. Lewis acids can promote reactions with carbonyls, for instance, giving homoallylic alcohols. You can even do intramolecular versions to make rings.
And this all connects back to the Peterson elimination too, right? Using silicon to make alkenes.
Absolutely. The Peterson is a dedicated alkene synthesis based on eliminating a beta-hydroxysilane. It's very good for making specific types of alkenes, like terminal ones, regioselectively.
Okay, we've covered a lot of ground with sulfur and silicon's unique abilities. Let's try to tie this together now with a major challenge in synthesis.
Yeah.
Controlling alkene geometry. E versus Z. Why is it so critical, and how do S, Psi, and P help chemists nail it?
It's absolutely critical because E and Z isomers, geometrical isomers, are different compounds, period. They could have different melting points, boiling points, reactivity.
Like dimethylmalate and fumarate. One's liquid, one's solid.
Perfect example. And crucially, different biological activity. The book mentions juvenile hormone for insects. Only one specific EZ combination is really active. If you make a mixture, it's much less effective, and separating them can be a nightmare.
So you really want to make just the isomer you need from the start.
Ideally, yes. That's the goal of stereoselected synthesis. There are sort of four main ways chemists approach controlling alkene geometry.
Okay, what are they?
1. Use existing structural constraints, like
Yeah.
in small rings. 2. Use thermodynamics. Let the system settle to the most stable isomer, usually E. 3. Design stereoselective reactions, kinetic control, where one pathway is just faster. 4. Use stereospecific reactions, where the starting material stereochemistry dictates the product's stereochemistry.
Let's unpack those. Strategy 1. Structural constraints, like rings.
Yeah, in a 5 or 6 membered ring, a double bond pretty much has to be cis, Z. You can't easily fit a trans double bond in there. Chemists exploit this. E.J. Corey synthesis you mentioned earlier.
The insect hormone one.
Right. He used a Birch reduction of an aromatic ring, which naturally sets up cis double bonds, and then carefully cleaved the ring to keep that Z geometry intact. Very clever use of inherent constraints.
Okay. Strategy 2. Equilibration. Making the more stable E isomer.
Usually, acyclic E isomers are more stable than Z isomers because there's less steric clash between the substituents. Now, pi bonds normally lock geometry, but under certain conditions, maybe with trace acid, base, or even light and iodine, you can get temporary, reversible additions across the double bond.
Which allows rotation.
Allows Greeves rotation around the single bond, then elimination reforms the double bond. Over time, this equilibrium favors the formation of the more stable E isomer. It's actually related to how vision works. 11-cis retinal in your eye gets hit by light.
Isomerizes to the all-trans form.
Exactly. That shape change triggers the nerve impulse, so light can interconvert isomers.
Cool connection. Okay, strategy 3. Stereoselective reactions,
Yeah.
adding things to alkynes.
This is a big one. You start with a triple bond. To get a Z-alkene, you need syn addition of hydrogen, both H's adding to the same face. Lindlar's catalyst does this beautifully.
That's the palladium on calcium carbonate poisoned with lead acetate.
That's the one. Gives Z-alkanese cleanly, used for the Japanese beetle pheromone. Now, to get an E-alkene, you need anti-addition.
Opposite faces.
Right. The classic way is dissolving metal reduction sodium in liquid ammonia. Goes via a radical anion mechanism, delivers the hydrogen's anti, gives E-alkanese.
Also lithium aluminum hydride for some specific cases. Propergylic alcohols.
Yeah, Lyl-H4, or red oil reduction of propergylic alcohols, often gives E-alkanese selectively. Important for things like sphingosine.
Uh-huh.
And remember, our silly friends, you can reduce alkynyl silanes too. Lindlar gives Z-vinyl silanes, red oil gives E-vinyl silanes.
So silicon helps guide the reduction outcome too. What about stereoselective eliminations beyond just standard E2?
Sulfoxide elimination's a neat one. If you have a sulfoxide next to an electron withdrawing group, you can gently heat it, and it undergoes a syn elimination. The sulfur and a beta proton leave together.
Forming a double bond. Syn elimination, like the Wittig.
Syn elimination, yes. It's good for making double bonds next to carbonyls, for instance, used in the queen bee substance synthesis. Selenium versions, solenoxide eliminations work even more easily, often at room temperature.
And then there's the Julia olefination. That sounds important.
Oh, it's very important. It's a sulfur-based reaction, but it's connective. It joins two different molecular fragments together to make an alkene.
And its specialty is?
High E selectivity. If you need to make an E double bond by connecting two pieces, the Julia is a go-to reaction. The mechanism involves a sulfone-stabilized anion adding to an aldehyde, forming an intermediate beta-hydroxysulfone.
Okay.
Then that gets derivatized and eliminated. The key is that the elimination pathway strongly favors the E-alkene, even if the intermediate steps aren't perfectly stereo-controlled. There are also newer one-pot versions, like the Julia Kosiensky, that are even more efficient.
Okay, that covers stereoselective. What about strategy 4? Stereo-specific reactions, where the starting material's configuration is key.
Right. Standard E2 elimination is stereo-specific needs anti-paraplanar geometry. And remember the Peterson elimination we talked about with
The
Philippine?
beta-hydroxysilane elimination?
Yes. That could be beautifully stereo-specific and stereo-divergent. Acid conditions favor anti-elimination. Base conditions favor syn elimination.
So from the same intermediate alcohol, you can get either the E or the Z alkene just by changing the reagent.
If you can make a single diastereomer of that starting alcohol, yes. Acid gives one alkene isomer, base gives the other. Incredible control.
Which brings us finally to what the book calls perhaps the most important way of making alkenes, the Wittig reaction.
The Wittig. Can't talk alkene synthesis without it. We know the basics. Phosphonium salt, deprotonate to get the alkene, the phosphorane,
Which attacks a carbonyl.
forms that square intermediate, the oxophosphate.
Which collapses to the alkene and phosphine oxide, driven by that PO bond.
Exactly. It's conceptually a syn elimination, like the base promoted Peterson or the sulfoxide elimination. But
Yeah.
the stereoselectivity is where the real story is. It depends crucially on the type of Lilid.
Unstabilized versus stabilized.
Precisely. Unstabilized Lilid's ones, where the Lid carbon just has alkyl groups or hydrogens, are reliably Z-selective.
Z-selective. Why?
It comes down to the kinetics of forming the oxophosphate intermediate. For unstabilized Lilids, the pathway leading to a syn arrangement in the oxophosphate is faster, kinetically preferred. That syn intermediate then collapses stereospecifically to the Z-alkene.
Like in the capsaicin synthesis example, making the hot stuff in chilies.
Exactly that. They needed a Z double bond, used an unstabilized Wittig. But if you use a stabilized Lilid,
One with an ester or ketone or cyano group pulling electrons from the halide carbon.
right, those are E-selective.
E-selective, so the opposite outcome. Again, why?
Again, it's kinetics, but the stability changes things. For stabilized Lilids, the initial addition to the carbonyl is often reversible, and the transition state leading to the anti-oxophosphate intermediate becomes favored. That anti-intermediate then collapses stereospecifically to the E-alkene.
So unstabilized gives Z via synoxyphosphate. Stabilized gives E via anti-oxyphosphate.
That's the general rule, yeah.
Mhm.
Variations like the Horner-Wadsworth-Emmons HWE reaction using phosphonate esters instead of phosphonium salts are particularly good for making E-alkenes from stabilized Elids. The bombical synthesis, the silkworm pheromone, use both types to get the specific E-Z geometry needed. Shows the power and contrast beautifully.
What an amazing tour. Sulfur, silicon, phosphorus. They're not just side characters. They're seriously powerful tools for building molecules with incredible precision, especially for nailing that tricky, easy geometry.
Absolutely. They offer reactivity patterns that carbon, nitrogen, and oxygen just can't match. Stabilizing anions, acting as superprotons, driving specific eliminations. It's a whole different toolbox.
It really speaks to the elegance of chemistry, doesn't it? How these subtle differences in where an element sits on the periodic table open up completely different reaction pathways.
It really does. It lets chemists design syntheses with remarkable control, building complex structures, sometimes mimicking nature, sometimes creating totally new things.
So maybe next time you encounter something with sulfur or silicon, you'll think a bit differently about the precise chemistry they enable.
Hope so.
Thank you, everyone, for joining us on this deep dive, and thank you for being part of the Last Minute Lecture family.